So today we're going to talk about probability and inferential statistics. So let's talk first a little bit about probability. What is it and why it's important? We talked about it just a little in Chapter 5 with z-scores, but probability is the study of the likelihood or uncertainty that something will occur. And probability plays a critical role in most professions and even in our everyday decisions. As we all know, we can never be 100% certain about anything, ever. However, probability helps us to determine how certain we can be. We can be certain to a degree, and that's where probability comes into play. So, believe it or not, most of the decisions you make are probabilistic. For example, how likely are you to get to class on time? What is the probability that you'll get an A or a B in this class? Or what is the probability that I will get an A in this class and an A in, say, your social psych class? Well, all of those things can be determined using probability. Now, probability is super important for interpreting our findings, and we saw that a little with z-scores, right? Well, probability will continue to play a role in this class, particularly when we conduct inferential statistics. When we are testing a hypothesis in science, we're testing the likelihood that a particular research outcome could result from random sampling or a real effect. Computing probability is simply dividing the total number of ways a particular outcome can occur by the total number of possible outcomes. And probabilities are expressed as proportions. We can base how certain we are on our probability values. And probabilities range from 0 to 1, always in the positive. And the closer to 0 a number is, that means we can be almost certain this event did not occur by chance. But a probability value closer to 1 means that we can be almost certain the event did occur by chance. So let's compute a few examples. So first we have drawing a red card from a deck of cards. Well, there's 52 cards in a deck of cards, and 26 of those are red, half of them. So if you divide 26 by 52, you'll get 0.5 or 50%. So you have a 50% chance of drawing a red card from a deck. Now in the next example, you're going to be taking the total number cards. So this is your standard numbers in a deck of cards, not including ace, jack, king, or queen. That's 40 number cards divided by 52 total cards, and that gives you a value of 0.78, or 78% chance that you'll draw a number card from a deck of cards. Next, we have what is the probability of drawing a 7 from a deck of cards. Well, there are 4 7s, one for each suit. Divide that by 52, and you get 0.08, or 8%. Even more specifically, drawing the ace of spades from a deck of cards. Well, there's only one ace of spade in a card deck, so divide that by 52 total cards, and you get 0.02, or a 2% chance of drawing that card. So let's just recap this again. How much certainty we have depends on our exact probability. A p-value, or probability value, closer to 1 means that we're almost certain this occurred by chance. A p-value closer to 0 means that we're almost certain this is not occurring by chance. So let's look at some examples. So if we have a p-value of 0.89, then we know that our effect most certainly occurred by chance. But if we have a p-value of 0.02, then the effect almost certainly did not occur by chance. In statistics, we set our probability value, or our alpha level, as you'll hear it called, at p less than 0.05, so that there is a less than 5% chance our findings occurred by chance. And this will make more sense as we start working on z-test and other inferential statistics. All right, so as I've mentioned, we discussed these scores in Chapter 5, but let's recap a little bit. Z-scores tell us how many standard deviations a person is in relation to the mean. And how does that relate to our normal curve? Well, those z-scores can be indicators of how likely someone is to score above or below the mean, as well as a few other details involving probability. Now, I want you to take a second and pull out your textbook and go to page 429. Go ahead and pause this video if you need to, and then press play again when you have that page pulled up. We have 3 columns of information on this page. First, the far left column tells us the z-scores ranging from 0.00 to 4.00. The middle column tells us the probability of a score occurring between the mean and the indicated z-score. And the far right column tells us the probability of a score occurring beyond the z-score, which is what we've done in our practice problems. Do you see how the proportions are identical on both sides of the positive and the negative curve? So we can determine probability using the normal curve and information about our z-scores. So what is the probability that a z-score will be higher than positive 1.64? Go ahead and find that number in your column. Look at the corresponding column in the middle and to the right, and you have a value of 0.05 or 5%. Now, what is the probability that a z-score will be lower than negative 1.64? Well, if you'll look, it's the same value, 0.05 or 5%. So despite directionality, the probability of that occurring is the exact same. So we've looked at how we can take a z-score and determine certain probabilities, right? Well, you can also reverse engineer a z-score based on your desired proportion, and we use the same table in the back of the book to do this. So for example, if we want to know what z-scores correspond with probabilities of 0.05 or lower, look at the far right and find the probability of 0.05. Right? That aligns with the z-score of 1.64. Do you see how every score after 1.64 has a probability lower than 0.05? When we move into inferential statistics, we'll talk about critical values and these cutoff points associated with our z-scores. Now, moving on a little bit, probability is also related to hypothesis testing. So let's review. What is a hypothesis? Well, a hypothesis is our prediction that we make that is a tentative proposition about relationships between variables. So again, a hypothesis is simply a tentative proposition about a relationship between variables. And we can test a hypothesis empirically. It must be stated in a way that can either be confirmed or refuted, which means, proven not true. So we test our hypothesis and use probability to determine how likely or unlikely a relationship is to occur by chance. And this makes more sense when we look at a real life example, so we'll do that now. So here we have the research question: what is the relationship between violent video game playing and aggression? What would you hypothesize here? Just take a second and think about it. Well, a lot of people would hypothesize that the more time spent playing violent video games, the higher aggression will be. So the rub of hypothesis testing. So when we have a hypothesis, we want to test it, right? It wouldn't really matter if we weren't trying to test it. So hypothesis testing is what we call this. We use statistics to provide support for our hypothesis. Now we know you cannot demonstrate truth beyond a shadow of a doubt. We can never prove anything. However, we use statistical techniques to instead show something is false. So we work a little bit backwards in the sense that we use statistics to help demonstrate that it is unlikely there is no relationship. The effect is not nothing, is a quote I like to use to think about this. But honestly, right now, it probably doesn't make a lot of sense, but we're getting there. Now, what is the difference between a null and alternative hypothesis? Well, your null hypothesis is the prediction that there is no relationship, and your alternative is a prediction that there is a relationship. And for each research question that you're testing, you'll need to state both a null and an alternative hypothesis. So we're going to look at each individually. The null hypothesis, which you'll also see notated as H0, the null hypothesis is a prediction that there is no relationship between variables. So for our video game example, our null hypothesis would be there is no relationship between video game violence and aggression. The null is applicable for many research questions, like those taking drug X will not differ from those who took the placebo. Now, the flip side of this is the alternative or research hypothesis, which is notated as H(a). So there is a prediction that there is a relationship between variables. Now, this is the one we want to support, right? We want to find a relationship. So in hypothesis testing, we use inferential statistics to try and reject the null hypothesis. If we reject our null hypothesis that there is not a relationship, then we can support our alternative hypothesis, which states there is a relationship. So back to our real life example. For our video game violence example, if our null hypothesis is that there will not be a relationship between video game violence and aggression, what is our alternative or research hypothesis? Well, it is that there will be a relationship between video game violence and aggression. For the drug example, if our null hypothesis is that those taking drug X will not differ from the placebo group, what is our alternative hypothesis? That those taking drug X will differ from those taking the placebo. And we're going to work a few more examples of this so that it's very clear to everyone. So here are some extra examples. Is there a negative correlation between self-esteem and jealousy? Well, our null hypothesis here would be that there is not a relationship, a negative correlation between self-esteem and jealousy. Our alternative hypothesis is that there is a negative correlation between self-esteem and jealousy. Now this question is, do kindergartners participating in a reading intervention outperform those who do not participate in the reading intervention? So our null hypothesis will be that there will not be a difference between kindergartners who participate in the intervention and those who do not participate in the intervention. But our alternative hypothesis will be that there will be a difference between kindergartners who participate in the intervention and those who do not.
So what is the difference between a one- and two-tailed test? Let's look at the definition first. A one-tailed test is an alternative hypothesis in which the researcher predicts the direction of the expected difference between the groups. All right? And a two-tailed test is an alternative hypothesis in which the researcher predicts that the groups being compared differ but does not predict the direction or the difference. So stated simply, the biggest difference between a one-tailed and a two-tailed test is simply a one-tailed test has a direction in mind. So let's take a look at that. So one-tailed tests are stated in a directional way. Now remember that with our null hypothesis, we're basically stating that there will be no relationship between two variables or no differences between groups. One-tailed test means our alternative hypothesis will be stated with a specific direction in mind. For correlations, for example, we could expect a positive or a negative relationship. And when we're looking at group differences, we could expect a direction of differences between the two groups. So did one group do better or worse than the other group? Let's take a look at some examples. Now, for correlations, a good example of a one-tailed research hypothesis could be There will be a positive relationship between the amount of alcohol consumed on St. Patty's Day and sick days taken by employees on 3/18. You could also say there will be a negative relationship between how many miles someone runs in a week and the chances of cardiovascular problems. So you see in both of these examples, we have the language positive or negative, giving us an indication of the direction we expect this relationship to have. Now for group differences, we could say that students who participate in group study sessions will do better on their exams than students who do not participate in group study sessions. We could say students who have social support will experience less stress during finals than students who do not have social support. So again, we see where we're saying here that they will do better on their exams or they will experience less stress. We have a direction in which, or a way in which we think these two groups will differ from the beginning, okay? Now, we don't always have clear directional hypotheses. We may expect differences, but we might not know what they will be. Can you think of some examples of this? One example that I like to think of is basically anything dealing with a drug treatment. So for example, if you're testing a new drug or levels of a new drug on participants, you may expect differences between the two groups or between the levels of the drug, but you don't know how those differences will exist, how will they actually manifest in your data. So this is where a two-tailed test comes in. This is a research hypothesis stated in a non-directional way. So we expect a correlational relationship, like IQ will correlate with problem solving, or we expect differences between our two groups. The treatment group will display different eating behaviors relative to the control group, but we have no directionality here. We're not predicting a positive or negative relationship. We're not expecting one group to do better, worse, faster, slower than another group. We simply have no direction here. We're just testing for differences or just testing to see if a relationship actually exists. So, some examples of this, and I tried to mirror these off of the one-tailed example so you guys can kind of get a clear idea of how these are different. So there will be a relationship between the amount of alcohol consumed on St. Patty's Day and sick days taken by employees on 3/18. There will be a relationship on how many miles someone runs in a week and the chances of cardiovascular problems. So neither of these correlational relationships are being predicted with a certain direction in mind. We're simply just stating we think these two things may be related to one another. For our group differences, there will be a difference in exam scores between students who participate in group study sessions and students who do not participate in the study session. Or there will be a difference in stress levels between students who do have social support and students who do not have social support. So again here, we're expecting differences between our two groups, but we don't really know what those differences are going to look like. We're not predicting that someone will do better or worse, faster or slower, anything like that. Here we're simply just saying we think a difference will exist. All right, so related to hypothesis testing, we have type 1 and type 2 errors. Now, our textbook defines a type 1 error as an error in hypothesis testing in which the null hypothesis is rejected when it is in fact true. Now, a type 2 error is an error in hypothesis testing in which there is a failure to reject the null hypothesis when it is in fact false. So, type 1 and type 2 errors are something that researchers are always concerned with. Every single time we conduct hypothesis testing, we run the risk of committing either a type 1 or a type 2 error. A type 1 error has occurred when we conclude that there is a difference or a relationship that does not truly exist. So if we reject our null hypothesis and support our alternative hypothesis, but in reality that alternative hypothesis is not true, we call this a false alarm error. Conversely, a type 2 error has occurred when there is a true effect, difference, or a relationship, but we failed to see it. So here we would fail to reject our null hypothesis, meaning we support the null hypothesis, when we should be supporting our alternative hypothesis. And this is referred to as a miss. So let's look at these two together, all right? So type 1 is a false alarm. This would be rejecting our null hypothesis when we should fail to reject the null hypothesis. And a type 2 is a miss. This would be failing to reject the null hypothesis when we should be rejecting it, okay? And this will all start to make a little bit more sense as you become more comfortable with hypothesis testing. So here's an example research question. What is the relationship between violent video game playing and aggression? Our null hypothesis in this situation would be that there will not be a relationship between violent video game playing and aggression. Our alternative or our research hypothesis would be there will be a positive relationship between violent video game playing and aggression. Now, is this a one-tailed or a two-tailed test? It's a one-tailed test. We have the positive language in our research hypothesis, which is indicative of a one-tailed test. We have directionality here. Okay, so when we conduct hypothesis testing, there are technically 4 combinations of results we can achieve, and we're going to go through each one. At the top of this figure, you'll see that we have 2 conclusions that a researcher can assume after computing statistics on our data. So after we've determined our hypotheses, collected our data, we've analyzed our data, we have 2 choices. We can fail to reject our null hypothesis, or we can reject our null hypothesis. On the left side of the screen, you will see the true nature, the true state of nature in relationship to our hypotheses. So this means despite what we've run, despite our calculations, despite what our data is saying, in reality, is this null hypothesis true or is this null hypothesis false? Okay, so let's say we failed to reject our null hypothesis, meaning that there is no relationship in our data, and in reality, there is no relationship. Your HO is true, right? This is a correct decision, okay? If we fail to reject our null hypothesis and then that null hypothesis is true in nature, we've made the correct decision. Now, the same can be said for when we reject our null hypothesis, stating that there is a relationship, and in reality, there is a relationship. Again, we've made the correct decision here. We've rejected our null hypothesis. We're supporting our alternative hypothesis by saying there is a relationship somewhere. And the true state of nature is that the null hypothesis is false and there is a true relationship. Okay, so these are the 2 correct decisions that you can make at the end of your research study. Okay, but what happens if we reject our null hypothesis, meaning that there is a relationship, but in reality, our null hypothesis is true and there's no relationship? That's a type 1 error. Now, what happens if we fail to reject our null hypothesis, meaning there's no relationship, but in reality, our null hypothesis is false and there is a relationship? Well, that's a type 2 error. So these are the 4 decisions that you can come to after conducting hypothesis testing. We obviously strive to make the correct decisions, but I wanted you guys to see how easy it can be to make a type 1 or a type 2 error. Now, which error do you think we worry about the most in psychology and why? Well, as we've discussed several times, we tend to take a conservative approach, right? We would rather miss a true result, type 2 error, than conclude there is a meaningful effect when there is not one, a type 1 error. So we would rather miss a result than have a false alarm. Now this relates back to something we covered in, I believe, chapter 5 on descriptive statistics. So remember with our standard deviation formula, we use n minus 1 to account for the variability in the population. Well, doing so, using n minus 1, our total number of participants minus 1, is also a way that we protect ourselves from committing a type 1 error. So going back as early as standard deviation, we are working to protect ourselves against making a type 1 error. Okay, so We've talked a little bit about inferential statistics, but we've mostly talked about descriptive statistics in this course so far. Now, descriptive statistics are numerical measures that describe a distribution by providing information about the central tendency, the width or spread of our distribution, and the shape of our distribution. So this would cover things like mean, median, mode, range, standard deviation, skewness, and kurtosis. All of those things fall under the umbrella of descriptive statistics. Inferential statistics are a little different. They allow us to draw conclusions about a population based on the data collected in a sample, okay? So differential statistics allow us to describe our sample. Inferential statistics allow us to go a step further and relate our sample back to the population. Let's take a better look at this. So, inferential statistics are procedures for drawing conclusions about a population based on data collected from a sample. So we all know that we take a sample of the population for our research, and then we use that data to derive statistics. After we compute these statistics, we either have significant results or we had no significant results. When a result is statistically significant, we're referring to the probability that this effect or this result represents some genuine phenomenon in the population. It wasn't just a chance occurrence. These significant results obtained using inferential statistics help us to generalize beyond our sample to the population. Now, how do we know if we have a real, true effect? We bring it back to probability. So probability values are critical for determining if our effect is statistically significant, or said another way, if we can make an inference about the population based on our sample. Statistical techniques give us a result, such as a Pearson correlation, and they tell us the exact probability that we would get this result by chance. So what type of result is this? A correlation, specifically a strong positive correlation, right? We can also determine the exact probability that we got this strong result by chance. Here we have a p-value of 0.003. What does that probability value tell us? Well, using probability, we can determine how likely we are to get this result by pure chance alone. So coming around full circle here, if you have a probability value of 0.003, that tells us that only 0.3% of the time you could get this result by chance alone. So it is very, very unlikely or improbable that you would get this result from chance, meaning that it has to be something else. It must be due to a true relationship in the population. Okay, but how strict are psychologists when making decisions about our results? Does anyone know off the top of their head, I would typically ask you? Well, psychologists are pretty strict. We set an alpha level of 0.05. So you'll see P is less than 0.05 in a lot of journal articles and reports, and you'll see it a lot in this class. So if we have a result that is statistically significant, our probability value, P, will be less than 0.05, and this allows us to reject our null hypothesis. However, if our result is not statistically significant and our probability value or our p-value is greater than 0.05, then we fail to reject our null hypothesis. And we're going to work several examples of this, so it should become more clear to you guys, but this is just kind of getting your feet wet with it. So, relating your test statistic to a critical value. So the larger your effect, and this could be a large correlation or a large difference between two groups, this large effect typically signifies that your effects are unlikely due to chance. If your effect beats a cutoff score related to a probability value of 0.05, then it is considered to be statistically significant, okay? So this is an SPS output of some correlations between academic skills such as vocabulary, comprehension, reasoning. You can see the correlational value associated for the relationship and its corresponding probability value. But let's take a look. All right, so let's look at the relationship between vocabulary and comprehension. So this blue box right here. We have a correlational value of 0.698 and a corresponding probability or significance value of 0.001. When you're in SPSS and you see SIG, that is your p-value, okay? So we have a really large effect. A correlation of positive 0.698 is a very strong correlation, right? We also have a really low probability value, right? 0.001. That's 0.1% of the time this could occur by chance. So this is a very likely true effect. So what about the relationship between algebra and comprehension? Well, we have a pretty moderate effect size of 0.483 and a probability value of 0.036. So again, likely a true effect, as we could assume this would only occur by chance 0.4% of the time, right? So I just wanted you guys to get an example of how this looks, how the correlational values and significant values look. We will be doing this in SPSS further on in the course. So again, just want to kind of introduce you to that now. Okay, so this is a little foreshadowing to the steps of hypothesis testing. When you conduct hypothesis testing, you follow these same 4 steps every time. The first thing you do is construct your null and your alternative hypotheses. The next thing you do is set up your decision rule. So an obtained p-value must be less than the value associated with 0.05. We then collect our data from our sample and calculate our test statistic. Then we apply the decision rule that we set up in step 2. So we compare our obtained value with our critical value. And if it was less than 0.05, we reject the null hypothesis, thus finding support for our alternative hypothesis. Now, for exam 2, we really only focus on the first step of hypothesis testing, constructing your null and alternative hypotheses, understanding their directionality, whether you're going to be conducting a one-tailed or two-tailed test. However, all of this bleeds into each other, and I really wanted you, again, to see this before it pops up after exam 2. So let's practice a little bit with hypothesis testing. So here we have health psychologists expected a positive relationship between energy drink consumption and insomnia. What is the null hypothesis here? Well, there will not be a relationship between energy drink consumption and insomnia. Our alternative hypothesis: there will be a positive relationship between energy drink consumption and insomnia. Now, is this prediction directional or non-directional? Well, it's directional. We have the positive language here that lets us know we expect this relationship to be positive. Because we know we have a directional prediction, we know that we're using a one-tailed test. Okay? Cognitive psychologists expected that those receiving an additional cognitive load would read significantly slower than those who did not. What is our null hypothesis? There will be no difference between those receiving an additional cognitive load and those who did not. Our research hypothesis, or our alternative hypothesis, is those who receive an additional cognitive load will read significantly slower than those who did not. Now, is this prediction directional or non-directional? It's directional. We have the word slower, right? So they'll take more time to read, or they will read at a slower rate. This gives us an indication of what direction we're expecting. So again, we would use a one-tailed test. Okay, last example. Social psychologists expected a relationship between introversion and empathy. What is our null hypothesis? There will not be a relationship between introversion and empathy. Our alternative hypothesis is that there will be a relationship between introversion and empathy. Now, is this prediction directional or non-directional? Non-directional. We have no indication of directionality here. We simply think there will be a relationship. We're not sure if this will be positive. We're not sure if it will be negative. Therefore, we use a two-tailed test because we have a non-directional prediction. Okay?